In this video, we are going to talk about explicit functions. Explicit functions in Calculus 3. What this looks like for us is it looks like something like z is equal to a function f of x and y. Okay, so this should look, an example of this should look something familiar to you from Calculus 1. For example, you could write z is equal to x cosine of y, or you could write z is equal to xy, or you could write z is equal to x squared plus y squared. Okay, so these are your explicit functions, and they are dealt with. They're dealt with in the following way. If you create a table of values, the dependent variables here, the independent variables are x and y, acknowledged by being in the function. This function is a function of x and y. And then if you could specify the x and y, then you would be able to plug those values in to find z. So for example, in this function, when z is equal to x cosine of y, if you choose x is equal to 1 and y is equal to 0, it's no problem to find the xy value, the z value, given that x and y. So it would be 1 cosine of 0. Cosine of 0 is 1, so this is 1. And if you tried 0 and 1, x would be 0, cosine y would be 1. 0 times anything is 0. So what you find here is that when the functions are explicit, meaning that z is explicitly solved in terms of x and y, it's easy to get the z value given some xy value. So you'll find now that you have 2 points. These two processes have given you the point 1, 0, 1. This is the xy, z value, xy and z. And you also have the point 0, 1, 0. Okay, this is your xy, z value. Z. Okay, so you get the idea here. So what this means, notice that there's some terminology from our website on the intro material notes. There is some language along the lines of sets and subsets of R3 and R2. So what I'm trying to point out here with this example is that this is an example of this symbol right here, 1, 0, 1. This is a point in R3 because there are 3 entries here, an x value, a y value, and a z value. This is a point in R3. This is also a point in R3, okay, because there are 3 entries. Okay. So one of the things that we'd like to talk about here is that R3, this is the set of all points, x, y, and z, such that the values x, y, and z are in the real numbers, meaning anything that you pick, any numbers x, y, z that you pick here, 1, 2, 3, is in R3 because 1, 2, and 3 are real numbers. You could pick pi, log of 2, and then e squared. That would also be in R3. Okay. But observe the following. If your z value is not allowed to be anything in R, any real number, but is instead z has to be x cosine of y, then you've got something where you say you've got x, y, and z such that z can't be anything by itself anymore. It can't be anything. It has to be x cosine of y. What we have here is a set S that's called a subset of R3. How do I know it's in R3? Because if I pick an x value, 1, a y value, 0, and I can plug into this function to get the z value, which was 1, I can see here that I have three entries. This is in R3. Okay, so this set S, if you look at all possible points, what are all the possible points that satisfy this equation? Okay, so you could, this is one point on that in that set. So there's a thing called all the points in S you can think of graphically. You can think of that graphically as the graph of the set S. Okay? So this set S, okay, it can't possibly, it's not all points in R3 because, for example, notice the following. If I pick X to be 2 and I pick Y to be 5, right, then the Z value will be 2 cosine of 5. Right? So this is a point in S. Okay, this is a point in S, I'm sorry. Because, you picked any XY value and you get the Z out of it. Okay? So that makes it easy to create points. So now that you have 1 point, 1, 0, 1, 2, 5, 2 cosine of 5, and 0, 1, 0, if you could imagine doing this, picking your favorite X, Y, Z values, you could pick something, find a Y value, and you'll get a Z. You can pick something, pick a Y, find a Z. Pick something, pick a Y, plug those into the equation Z, and you'll get a number for Z. If you could put all those together in the X, Y, and Z, we know that there are 3 entries, so whatever we are plotting here is going to be some sort of subset of R3. It will make some sort of surface. Okay, what that surface looks like exactly is not really what concerns me so much, except at the moment that I'm more interested in whether or not you understand that when you see this function right here, Z is equal to X cosine of Y, you can think of this as an explicit function that you can use to make a subset of R3. If you really want to see the plot of this function, you can bring in Mathematica, right? You can make an explicit function which will define a subset of R3 in this case. R3. Okay, so let's do that now. That way you can see what the plot looks like. So I'm going to make a function. I'm going to hit here, and then those stars make a comment symbol, so I can now type in this function. Let's call this function f. Let's make it a function of x and y. That's what the underscores do, tell you what the independent variables are, and now make x times cosine of y. Okay. Hit shift return, and that will define this function. You can come back up here, hit return to do another line to this code, and you can say plot 3D. We are plotting 3D because this function x cosine of y is going to make a subset of R3. Okay, so I'm going to do a plot 3D, and you say plot the function f of x and y, and you plot it from x is say -1 to 1, or -1 to 1, and y goes from -1 to 1. So we have just what we should expect to happen here. Okay, what we expect to happen before I hit enter is that we told the computer that we are interested in looking at the x values from -1 to 1. Here are our x values, and we want the y values from -1 to 1. So you want to look at this little square and you want to pick a bunch of points in this square, right? Plug them into an XY table, find the Z value, okay? Get all the XYZ points out of there, and then put those on the plot. And so if you get enough of these points together, they will make some sort of surface. Okay? What does that surface look like? Well, you just have to hit Shift-Enter after you've typed this. And here is what the plot looks like. Oops, let's go from -1 to 1. Okay. So the x values go from -1 to 1, and the y values go from -1 to 1. Which is the x and which is the y? It's probably best if you say axes label goes to x, y, z. And now you've got which axis is the x, which is the y, and which is the z. So now you can move this around and manipulate it. Okay? So this function f, right, this function x cosine of y will make a subset of R3. This surface thing lives in three-dimensional space. Okay? So that's it for the explicit functions. Okay? That's it for explicit functions. And the rest go the same way. You can say, you can pick a z is equal to xy, right? You can view this as a subset of R3. This will make some set S, and it will make a set where the x, y, z values are not just any point in x, y, z space, but they are the x, y, z values such that the z value is x times y, whatever you pick for x and y. Okay. So, for example, like if x is equal to 1 and y is equal to 2, right? You could find the z value would be 1 times 2, which is 3. Okay? So the point 1, 2, 3 is in the set S. But what is not true, it's not true that 1, 2, 5 is in S. See, 1, 2, 5, this is in R3 because each of these 1, 2, and 3 are real numbers. But for it to be in the set S, this third value has to be the first value times the second value. So the only way you can get the last value to be 1, the first value times the second value, I'm sorry, 1 times 2 is 2. I don't know what I was thinking about. 1 times 2 is 2. So the only way you can get this number to be the first times the second is for the z value to be 2. Okay? So it is true that 1, 2, 1, 2, 1, 2, 3, 4, 5. It is true that 1, 2, 5, that is in R3, but the point that's on the subset is 1, 2, 2. That is the point that's going to be on your surface. This one is just some point in R3, but it is not on your subset. So if you want to see what this subset actually looks like, okay, we could make another function. Hit return. You could make a function, call it g of xy, and you could say that this is x times y. Okay? So what we just made here is z is equal to x times y. Okay. I hit return to do a plot of this thing, plot 3D. You can plot this function g, and let's plot this function g from say -5 to -4 to 4, and y from say -4 to 4, or -5 to 5, we'll say. And then let's put the labels on the axes so you can see which is the x and which is the y. So I need to type better. X, y, z. Hit enter. And here is what your function x times y looks like. Okay. so that we can see the x values going from -4 to 4, -4 to 4. We can see the y values going from -5 to 5. And if I can look at this point 1, 2, okay, here's the point. Let's take a look at the top here. Here is the x value of 1. Here is the y value of 2. So it's about that point right there. So if you can focus on this point as I rotate the graph, it's right about here. It's right about here. You can see that that would be a value of about, rotate out to be about 2.
Did you get my email?
1 second.
Oh, I'm sorry.
Okay. Picking back up, we did this example was z is equal to x times y and showed what point was on the surface, and the point 125 was not on the surface. And so that's it for explicit functions, really. The only thing that changes is the actual formula, and if the formula changes, the picture over here will change also. And, you know, it's just, from my perspective, the idea is to make sure you can count the variables so that you know whatever you're looking at, z is equal to f of x, y, that you know in your mind that that is going to be something, some surfacey, not very technical language here, but some surfacey object in R3. If you want to know exactly what that surface looks like, pick a specific function here and do the plot of it. So that's it for explicit functions. The next video will be implicit functions.